Hello, everyone. I'm Brian Retford with Risk0, and I'm here to talk about using zero-knowledge cryptography to build more complicated and interesting applications. So I'm going to just do an intro of the company, talk about CLOBs in particular. So we're going to examine this idea of building more complicated applications through the lens of a central limit order book. And then I'll talk a bit about general purpose ZK computing and what we mean exactly by this idea of a ZK coprocessor. And then we'll go over some data and take a look at what a CLOB that's built using a ZK coprocessor looks like. Okay, so Risk0, if you're not familiar with the company, we are on a mission to make using ZK as easy as possible and really utilize the technology to its maximum degree. And we've done that by building the first open source general purpose ZK VM, and we'll get into what all that means. The company's mostly out of Seattle. Yeah, and we've known each other for a long time. And we use ZK Starks. So our sort of core technological innovation is the Risk0 ZK VM. And this is similar to sort of a ZK EVM, which takes in Solidity code and executes that in an EVM environment. Our ZK VM takes in code written in Rust, C++, and now Go. And in the future, we'll support as many languages as we possibly can. And then we use standard compiler toolchains, so LLVM and GCC, to compile this code down into an image that uses the RISC-V microarchitecture, which you don't really have to worry about. It's just a real microarchitecture. Runs this code and produces a ZK receipt. So it's a ZK VM that can execute arbitrary code. So rather than, say, learning any number of specific sort of circuit compilation languages, you can, if you use Risk0, just write your sort of programs in Rust, C++, use whatever libraries you want, and not really worry about the specifics of the ZK circuit. So that's been open source for almost a year, about as long as the company's been around. And we are now here at ETH Denver launching a new service called Bonsai, which lets anybody use this ZK VM sorry, somebody was waving back there, distracted me. So Bonsai lets anybody use this general purpose ZK computing platform in a way that posts the results on chain and lets you offload a bunch of your complex logic onto this network. So I mentioned at the start that we're going to be considering building more complex applications through the lens of a CLOB, or a central limit order book. So for people who aren't familiar with CLOBs, I think the SEC introduced them about 20 years ago. And they basically let people, this is like your standard stock market system. You place orders that you would like to buy something at a certain price, and other people say they would like to sell things at a certain price, and you end up with a sort of order book full of a bunch of desires for people to buy various things at various prices, and then when there are matches, the trades are executed. So CLOBs handle the vast majority of worldwide trades. So NASDAQ and other major stock exchanges all use this format. So it's it's actually really impressive how far Uniswap and DEXs have gotten, and I'm sure they'll keep moving forward, but right, the NASDAQ processes about 400 times as much volume as Uniswap right now. So CLOBs are generally considered one of the most fair and sort of market efficient mechanisms for doing trading and exchanging. And I would say, at least in my opinion, DYDX is sort of the most prominent semi-blockchain example. I say it's a semi-blockchain example because the sort of order book matching logic doesn't actually run on chain. And if it did, at least by their numbers, it would be about 100 times more expensive than Uniswap. So about $800 a trade when gas is pretty cheap. So it's an interesting question. I mean, why are there no CLOBs on chain? I guess it's kind of obvious that the gas is very expensive. So when thinking about sort of the limitations of current chains and how ZK can address them, I thought it was useful to take a look back and think about some of the obvious examples of where demand for block space has gotten so high that it basically forces all normal users out, and also wastes a lot of money, and I think really holds the ecosystem back. There's a sort of bizarre dynamic where if your application becomes very successful, the cost to use it rise and kind of acts as a natural buffer on the limits of what your application can achieve. So I think this is a dynamic that, on L1, on L2, anywhere, ideally we'd be able to get rid of, and you wouldn't have these kind of ULab type situations. I think it's important to look at Uniswap. It costs about $8 a swap, and goes through about $1 million a day in gas fees, all of which are, not actually useful for the users themselves or Uniswap. It's critical infrastructure in crypto, obviously, for price discovery, but generally speaking, CLOBs are better at setting prices. So I think there's also some recent examples. I guess this happened 2 weeks ago. Apparently somebody told me it was something to do with people dumping Blur, but temporarily, you couldn't do anything unless you wanted to spend a lot of money to do it. This actually doesn't have anything to do with block space, but I thought it was funny, and I'm actually really curious what happened to Solana 2 days ago. So if anybody knows, they could tell me later. Okay, so looking at a CLOB, I don't want to get too far into the exact algorithms people use. We'll look at a bit of the matching in a second. But it effectively scales in n log n or polynomial time, depending on how you implement it. And what this means is that unlike Uniswap, where the sort of cost per transaction isn't really affected by volume, in CLOBs, the more orders you have, the more orders you have to match. So the costs in terms of gas rapidly scale up to the point where, at a reasonable volume, you're actually using up an entire Ethereum block. If you write your CLOB, in Solidity and run it totally on the EVM. So these are measurements from a CLOB that we wrote that somebody very skilled in Solidity wrote. So we're pretty confident, it's not possible to write a CLOB that's more efficient than this on the EVM. So don't need to get into this too much, but if you're curious why it's n log n, it's really m. Every new order has to be compared to all of the open orders, which are generally stored in sort of binary tree or a Merkle tree. So that's where you get these kinds of scaling numbers. Cool. So with all that in mind, I want to talk a bit about general purpose ZK coprocessing and what we mean by this and how it can help solve the sort of gas problems that, that we were observing with these kinds of applications earlier. So first, I want to talk a little bit about just what ZK does in general, because I don't know, it's hard to tell how familiar people are or will be with any of this. But this is sort of an example of how ZK, at least in our system, works. You have sort of a host program that runs ZK code, which gets verified and produces a receipt, which is a much smaller it's a very fixed size blob that certifies that a particular program that you may or may not reveal, when run with a particular set of inputs, which you also may or may not reveal, produces a specific output. So in this example, you could imagine maybe running Doom in your ZKVM guest and having the data from your host actually be mouse movements. So you could effectively prove that a given speed run of Doom actually came from Doom's source code without revealing actually how you did it. So you'd have a sequence of mouse inputs that would be your sort of private data input. The code is known, it's the Doom source code. You run it, it produces a very small receipt that can be verified anywhere. Like one lens on ZK. So there's this process of verification, and this is pretty important. So generating these proofs is very expensive. It's gotten progressively less expensive, and I expect it to continue to get progressively less expensive. But it's still like somewhere between 5 and 10 orders of magnitude more expensive than not doing ZK. However, verifying these proofs is generally very cheap. It can be very expensive on Ethereum, depending on which cryptographic system you're using. But we won't get into that. It's very important, though, that you can verify these things in constant time, independent of how long of a program you were verifying. Yeah, this is just like a little graphic that explains how this works. So this is an example of a RISC-0 example program from our open source repository. And it basically lets a user prove that they know the prime factors of a large number without revealing those numbers. This is a classic problem in cryptography. It's very difficult to factor very large numbers. So you generally, knowing the factors of a very large number sort of is a way to prove, a secret that can be used in various cryptographic operations like creating public and private key pairs. So this example really just reads in 2 inputs that are kind of hidden from the user, and then commits to this journal the output, which is, in this case, I think 391. So if the user passes in these 2 numbers, they can effectively prove, that they'll tell someone else, here is like 391, and I know the factors for that. Now, obviously, factoring 391 is not hard. However, if you start using, 256-bit integers, then you start to get the kind of cryptographic security that you would expect. So this is just like a simple example of how you can use ZK to prove private knowledge, without revealing that private knowledge. There's another example, and this is starting to get into where I think what we're doing really shines, and this is actually all the code you need to prove that a given chessboard that's serialized in a standard sort of chess format contains a checkmate without actually revealing what that move is. So this is utilizes this checkmatey Rust library to basically do all the complicated sort of chess logic. And you can basically create these kinds of ZK proofs from existing libraries very trivially. So hopefully this provides somewhat of a lens on sort of what ZK is and what ZK VMs can do. So Bonsai, the other system that I mentioned, which is kind of the focus of the company right now. I mean, we're always focused on improving the ZK VM, but this is what we're actually launching here at ETH Denver. And it's basically a mechanism whereby you can write the parts of your application that focus on on-chain assets in Solidity exactly as you normally would, but then you can write the sort of code that actually does complex things, like order book matching, or running a game engine, or doing a lot of data processing off-chain. And there are a couple other projects doing really cool stuff in this space, like Axiom. They have a quite different approach from us, but nonetheless, I think this is going to be a modality that we start to see become a lot more prevalent, which is compute doesn't necessarily need to happen on chain because it's not necessarily what chains are good at. Chains are good at moving assets around. So Bonsai has sort of the machinery involved such that if you were to interact with an application on chain, it will eventually trigger the execution of this ZK image and prove it, and then we'll spit this output into something we call a universal rollup. A universal rollup is basically a summary proof of a ton of stateless computation. Excuse me. So in this case, the state actually lives in Ethereum. The state kind of gets transited into the ZK VM. It produces this proof, and then this gets rolled up to a single proof. So this lets every user of the system effectively share the costs of verifying the one proof across pretty much every chain. Our intention is to publish these proofs to every single chain. We're very focused initially on the Ethereum ecosystem. So this is like the weirdest thing about ZKs. Or at least kind of blew my mind when I realized this was possible. So in order to do this sort of universal rollup, because the idea is to be able to process, not 100 or 1,000 transactions per block, but millions or even billions of transactions per block. And the magic that lets you do that is this idea of recursive proofs. And recursive proofs, some people call this proof aggregation, and there are a lot of different techniques for doing this. But this is really the sort of magic that makes ZK rollups. And basically, if you have two proofs, you can run the verification of those proofs inside the ZK system, and it spits out one proof that effectively attests to both of those proofs. So you can compress two proofs into one proof. So as soon as you can compress two proofs into one proof, you can compress an arbitrary number of proofs into one proof. Well, I mean, that doesn't necessarily follow, but the math in this case works out. So you can actually do this. So when we're thinking about a system like Bonsai, the main sort of thing that limits the throughput and thus sort of the cost efficiency and also the complexity of applications people can ultimately build on it is really this recursion time. So this is the amount of time it actually takes to take two proofs and turn them into one, is one way to think about it. It could be 3 proofs, 4 proofs, 5 proofs, whatever. It's kind of gets into the specifics of the machine it's running on what makes sense. So we've spent a lot of time like heavily optimizing the recursion time because it fundamentally tells you how many computations you can fit into the next block, or say, with 3 blocks latency, you can almost certainly fit 1 million proofs into a single rolled up proof. But if you're talking about like a 4-second turnaround time, you can only, fit as many proofs into that 4 seconds as you can, reduce to a single proof in 4 seconds. So right now, I think we're still about 10 seconds per recursion, but it'll be like 2 pretty soon, and we expect that inside the year it will be down to like 100 milliseconds, which is enough time to get just really start including millions of sort of computations in a sort of single state root. There's going to be a bunch of decentralized sort of marketplace aspects to this, but we're not really focusing on that today. So I did mention, earlier that maybe one would want to like run Doom inside the guest, and then provided some examples, some pretty simple and trivial examples of code running inside the ZK VM. And since we released it, it's continually gotten more mature, but it's still like a very simple processor, I guess, in terms of its capabilities. So the way we think about it right now is that it's kind of like a fancy Arduino. It can address more memory, but it really runs at about 20 kilohertz on your laptop. We do have GPU acceleration, although there's a bit more work to do to really get more than the sort of 2 to 5x we see now. But we do expect, in the next couple months, to get to a point where the GPU acceleration gets you a lot closer to a megahertz than 20 kilohertz. Beyond that, once we sort of have this fast recursion, people call this like incrementally verifiable computation. We call it continuations. But it's this idea that you can split a computation, the proving of a computation up into a bunch of parts, prove them independently, and then use recursion to combine them. So this actually lets you run arbitrarily complex computations in a ZK context. So thinking about like proving that that this particular Linux kernel binary came from compiling all of the Linux source code with certain hashes with a compiler that hashed to a certain thing. These kinds of very, I would say, kind of out there ZK use cases will become possible, and we'll also be introducing the ability to address more memory sort of shortly. Moving into later this year, we expect to support like 2 gigs of RAM, and we'll open up our accelerator DSL language, which is sort of like Noir or like Leo, except for it's really focused on building accelerators that get attached to this general purpose chip. So the kinds of things that you're going to be able to do with Bonsai are going to continue to increase. However, I will say even a fancy Arduino is enough to run CLOB in a really interesting manner. So I'm going to talk about Bonsai, which is a CLOB implemented on top of Bonsai. So going back to this sort of chart explaining how Bonsai works. In this case, the CLOB contract, which exists in Solidity, is the Ethereum application. This is basically the application that lets people submit orders, and that effectively settles their transactions. In this case, the orders sort of flow through the Bonsai system into the ZK VM, where the order matching logic runs. And that is actually like 1,200 lines of Rust. I think the 1,200 includes tests. So doing this, and then the matches flow back to Ethereum, everything settles on chain. So what does this actually do to your costs for running a CLOB? Well, based on our measurements, it's basically 100 times cheaper to do things this way than using the sort of pure EVM CLOB, which actually puts sort of on Ethereum CLOB into the realm of feasibility, to the point where it's actually probably cheaper than Uniswap to actually do trades on a CLOB implemented this way. And you get to write your code in Rust, which not everybody loves, but you can use other languages as well. We'll support Solidity eventually too, but I guess we're all Rust heads. So one way to think about this in terms of costs is the CLOB that's written purely for the EVM, effectively 1% of the cost of it was involved in settlement, and like 99% of it is running the sort of matching engine. But the matching engine doesn't need to be run on chain. It can be run off chain in this kind of ZK co-processing modality. And that really shrinks the cost of your system to 50 to 100x in this particular case. And that's assuming, well, fairly healthy margins for the ZK co-processing systems. But yeah, especially as I think ZK is on like a Moore's law curve itself, beyond the sort of Moore's law curve of the underlying hardware that it's on. That combined with the sort of amazing work like Inganyama and Olvatan is doing in accelerating ZK, there are many other projects out there. I expect the capabilities of what you can do with these kinds of co-processing systems to just continually expand and sort of drive the costs of co-processing down even further. Which will really increase the kinds of things you can build to the point where you really could run, Doom effectively in an on-chain provable manner via ZK co-processing. So we have a bunch of examples of the ZK VM stuff. I think we have like 20 now. There's some really fun ones. Including proving that you know where Waldo is in an image and clipping it out without revealing where Waldo is. And then we have, for Bonsai, we have a way to build applications like this one in a purely local manner. It spins up like a EVM chain and all the necessary sort of components to actually develop these applications. The actual network, you can sign up for early access now if you want. We're hoping, I think we just started onboarding people today. Yeah, and it's a way to experiment with building far more complex applications than you've been able to build in the past without needing to migrate to a different chain. So in the sort of DYDX example, they moved to their own Cosmos chain and are still running all their order book logic effectively off-chain. And this is a way to kind of embrace the potential of running everything on chain without having to make all of the compromises that people have had to make. Yeah, got 4 minutes left, so I could do questions if people have any, or I could talk a little bit about some other cool things you can do with the ZKVM. Yeah? Take a picture of the QR code or go to r0.link/bonsai. The question was where you sign up, so that should be kind of obvious. Cool. Well, if there are no other questions, I'll be hanging out here for a bit if people want to just chat with me later. But I do want to talk about some cool things you can do that I expect people to start doing with ZK in the future. So one of them that I talk about a lot but still haven't gotten around to doing is the idea of like a ZK generative NFT. So what this looks like is an NFT where potentially the code that generates the art is private, So it's kind of like uncopyable in a sense, because you can prove that you own the code that generates it. The code that generates it could be like in a secure enclave, buried under thermite. I don't know, anything you want. But you can actually, by utilizing sort of ZK at scale, build really interesting new kinds of artworks that are effectively uncopyable. I'm really, really excited about private strategy games. So if people paid attention to any of this, Matchbox Labs recently released a new version of the 0x Monaco game, which I managed to misspell, called Battle of the Titans. And this game is sort of like Mario Kart, where the where the cart's abilities sort of exist based on like a weird marketplace. So they basically invited a bunch of teams to write strategies that would run for 100 or 1,000 turns privately and sort of determine what cars did at every step. So if you have like 5 cars racing each other, each of the teams submits their strategy, and they had constraints on how much gas the strategy could use, things like that. And they're run privately, so people basically can compete to see if they can, create the best strategy without revealing what they're doing. Now, Matchbox didn't do this with ZK for the last version. They just told people to trust them, which you can trust them, but it's not gonna enable these kinds of games to take off at scale until you can really prove that your strategies ran in the way that you committed to running them without, without trusting some randos. So I'm really excited about the ability to build new kinds of games like this, and there are actually a couple of people working on things in this realm, with us right now. All right, I have a minute left, so you could imagine at the limit, building robots for Doom and doing similar things to this. So I don't know where any of that is actually going, but it's really amusing to me that it's a possibility. Thanks, and we're having a developer meetup later tonight. I think it's fairly sold out, but if people really want to come, let me know. Thank you.